One of the keys in developing a simulation is to have a routine to generate random values for variables with specified random distribution, for example, uniform, exponential, or normal. This is done in two steps. First, a sequence of random numbers uniformly distributed between 0 and 1 is obtained. In the second step, the sequence is transformed to produce random values satisfying the desired distribution. This is sometimes called random variate generation. Let's take a look at how random number generators operate. The most common method is a recursive relation in which the next number in the sequence is a function of previous values. Here, the sequence of numbers is 10, 3, 0, 1, 6, 15, 12, 13, 2, 11, 8, 9, 14, 4, 5, and starts over again. If we divide by 16, we can get a sequence between 0 and 1 and scale it. The function used to generate the sequence is called the generator function. The value that we start with, x0, is called the seed. The numbers generated by this are pseudo-random in that they would pass a statistical test for randomness. We also have a cycle length of 16. Some generators do not repeat the initial part of the sequence, which is called the tail. So, what properties should we have for a generator function? Well, 1, it should be efficiently computable. 2, the period should be large. And 3, the successive values should be independent and uniformly distributed. We can determine property 3 using tests such as chi-squared, Kolmogorov-Smirnov, k-dimensional uniformity, and spectral tests. If you're interested in these are covered in data science curriculum and also in Chapter 27 of Raj Jain. There are several different types of random number generators. In this presentation, we will look at linear congruential generators, Tausworth generators, extended Fibonacci generators, and combined generators. Let's start with the familiar linear congruential generators. Way back in 1951, D.H. Lamer discovered that residues of successive powers of a number have good randomness properties. He obtained the nth number in a sequence by dividing the nth power of an integer, a, by another integer, m, and taking the remainder. The parameters a and m are called multiplier modulus. Lamer used a equal 23 and m is equal to 10 to the 8th plus 1 on the ENIAC. Many of the random number generators in use today are a generalization of Lamer's form. These generators are popular because they can be easily analyzed and certain guarantees can be made about their properties. The choice of a, b, and m affects the period and autocorrelation in the sequence. A couple of pointers if you're going to make one of these. The modulus m should be large since the period can never be more than m. For the mod m computation to be efficient, m should be a power of 2. If b is non-zero, then the maximum period is obtained if and only if m and b are relatively prime to one another. Every prime number that is a factor of m is also a factor of a minus 1, and a minus 1 is a multiple of 4 if m is a multiple of 4. A generator that has maximum possible period is called a full period generator. Not all full period generators are equally good. A generator with lower autocorrelation is preferable to one with a higher autocorrelation value. There are also different variants of these generators. For example, purely multiplicative generators, generators with m is equal to 2 to the k, and generators with m not equal to 2 to the k. The interest in random number generators has grown recently due to their cryptographic applications, where random numbers of certain lengths are required, for example, 48-bit keys. Such large numbers are produced using a random sequence of bits and dividing the sequence into strings of the desired length. In general, the Tausworth generator has the form shown on this slide, where c sub I and b sub I are binary variables with values 0 and 1, and the circle with a plus inside is the exclusive order. The generator uses the last q bits of the sequence and is called autoregressive sequence of order q, or ARQ. It has a maximum period of 2 raised to the q minus 1. We can also introduce a delay operator into this. A Tausworth sequence can be generated in hardware using linear feedback shift registers. For example, the polynomial x to the 5th plus x cubed plus 1 results in the generator b sub n is equal to bn minus 2 XOR bn minus 5. This can be implemented using the linear feedback shift register shown here. We have 6 registers, each holding 1 bit. On every clock cycle, each register's content is shifted out and the new content is determined by input to the register. From an autoregressive qubit sequence, we can produce random numbers of any desired length. Tausworth proposed to construct an L-bit random numbers x sub n using the bit sequence b sub n by dividing the sequence into successive groups of s bits and using the first L bits of each group as a binary function, as shown here. Tausworth generators have some interesting properties. The mean of the sequence is always 1/2, the variance of the sequence is always 1/12, and the serial correlation is 0. Most of the polynomials used for generating Towsworth sequences are trinomials with just 3 non-zero terms. In this case, the generation of each new bit requires just one XOR operation, which makes them very fast. A disadvantage to these generators is that while the sequence may produce good test results over the complete cycle, it may not have satisfactory local behavior. Another type of generator is the extended Fibonacci generators. A Fibonacci sequence is generated by the relationship shown here. However, this sequence does not have good randomness properties, as you may have guessed. So, an extension of this approach would be to combine the 5th and 17th most recent terms. This generator passes most statistical tests. To implement this, we would need 17 storage locations filled with integers, and we would set 2 pointers I and j to 17 and 5 respectively. Some of the integers will need to be odd in this sequence. On each successive call to this procedure, we execute the procedure which returns the next random number and updates the pointers. The add operation in the first line of this generator is automatically mod 2k in a k-bit machine with 2's complement arithmetic. The period of the generator is 2 raised to the 17th minus 1. So we've looked at linear congruential, Towsworth, and Fibonacci generators. It's possible to combine 2 or more random number generators to produce a better random number generator. Some techniques to do this are adding random numbers obtained by 2 or more generators, using exclusive order on the numbers generated by 2 or more generators, and then shuffling by using one sequence S as an index to decide which of several numbers generated by a second sequence should be returned. We should also take care in selecting seeds. Jain gives the following advice: do not use 0, avoid even values, do not subdivide one stream, use overlapping stream, and you can use seeds left over from previous replications. He also gives the advice to avoid random seeds, since you want to be able to replicate your results if you're making a simulation. There are some other things to note in terms of random number generators. 1, a complex set of operations does not necessarily lead to random results. You need more than a single statistical test to determine whether or not you're getting good randomness. Certain routines such as linear congruential generators can be reverse engineered. And bits of successive words generated by a random number generator are not equally randomly distributed. Thanks so much as always for watching.